Let us continue this afternoon talk. I need to say something about where Jacob works. So one of the things that this institute needs to improve is that it needs to improve also its spread throughout the United States. Namely, the previous events, there was some sort of not written but verbal complaint that it's always the East Coast and the West Coast and the Midwest, and not so much people of the south of the United States, whatever south means in this context. So also, not only we need to look people in South Latin America, but also in the south of the United States. And so we were doing our research, and we found Jacob. We were very happy. but the thing is all these things to somehow to fix them is difficult, no? Because you have to spread all these things, but then you go and look and spread your head, and people are localized in specific places. And so also the part of things we need to do is also to bring people from like throughout the United States. So we had to do this, and Jacob, I'm happy that you came from the University of South Florida, and in Tampa, and you drove, if I'm not mistaken, you drove to here, so it's very good. So thank you for coming. So Jacob is a PhD graduate from Texas A&M, and Rafael knows him from Mainz, I suppose, because he was also in Germany working with the Sinova group. So, and now he's a professor at South Florida. Welcome, and thank you for coming.
Thank you for the invitation, Rafael and Bernardo. Yeah, that's right. I drove about 4 hours from University of South Florida, which is 4 hours north of here, but there's only the Everglades, ever swamps, whatever, below. Yeah. Switch to the title, back to the title. So I have this tidal disorder in multi-band topological semimetals here. The quotations are very large because there's not any actual disorder. We want to keep this these block states in there. I'll explain what I mean there. Some of the funding acknowledgements, we have this young investigator work from the Air Force. We also have some Max Planck funding, and we also just recently got this control scholar from the Research Corporation. We also use computers and still in mines and also in the Lake Forest Center. And we have just started in the university this Florida initiative for emergent low dimensional quantum materials. My group, my postdoc, we started in December. He was actually working on a lot more on these topological things at the moment, but we're also doing his work, and then we have a graduate student, 2 graduate students here, and a soon-to-be graduate student. 2 members that just moved on. So we have Cole Gibson, who's now at Princeton, and Bushra Severe, who is kind of left science, but most of the work comes from these 2 here that have left the group. So in terms of disorder, what I mean here, the word I want to choose, looking at is when we go from this perfect system and we start to strain it in terms of going from this cubic case to a case that could be, the case that can be either tetragonal or have some rhombohedral shape that is not 60 degrees between angles. And then on the other hand, as we're using first principle calculations, also with quotes from there, depending on your eyes, we're also alloying this material using what's called a virtual crystal approximation. So this is effectively changing our model on how we look at the system. But still, we keep all of the case states diagonalized in this case. Any questions about that? You can do this experimentally through temperature, growth, and lattice mismatch, and throughout the presentation, we'll compare to experimental results of the same materials. So I've gone over introduction. Next, I want to go, the outline of the talk looks like something like this, where we go over some simple Hamiltonian that looks almost exactly like what Rafael showed earlier. We will go over this anomalous Hall effect in different regimes and compare that with this potassium vanadium antimony, which me and Rafael shared a paper on. And then lastly, we'll talk about this multi-band model for chromium platinum 3, which is this cubic compound. What's interesting there. So the simple Hamiltonian we can look at, this is very similar to what Rafael showed earlier. Typically we can write this term here, which is these sine terms, which is linear and k, and when you take the linearized model, this acts something like the spin-orbit coupling. This also gives you this Weyl dispersion on the node, and then you have some hopping in 3 dimensions, kx, ky, kj, and you have some magnetization that can depend on the space, and you have it coupled to the spin dot product. When you look at the energy eigenvalues, without the spin orbit term, you get something that's like this, and you can look at it along the kz path, where the kx to kg is 0, and then you can find out the range of the ratio of MO and G, which I think also Raphael showed, and it also tells you the position where this crossing happens. And so one thing that's interesting about that crossing, you have these inverted bands. This color shows a spin character. And another part that happens there is you get the anomalous Hall effect is maximized in terms of the local and energy of where that crossing is. Good. Any questions? What is the anomalous Hall effect? This happens in magnetic materials when you have in magnetic materials you have a mispopulation between spin up and spin down. And when you apply electric field that is perpendicular to that magnetic direction, you get what's called an anomalous Hall effect, which is a Hall effect that voltage is perpendicular to both that original magnetic field and this applied electric field. We can calculate that using the Kugel formula, and I don't go into so much detail because I think Raphael did a good job. And this is when we do that Kugel formula for that material, we get this maximized anomalous Hall effect in the vicinity of that crossing. And this anomalous Hall effect happens throughout between those two crosses, not only directly at that crossing. Good. All right. Let's go to the next one. Yeah. So. Some of the work that was done by many in the field over the last few decades, or last half a century, is this idea of this anomalous Hall effect and these different regimes that you can actually calculate the anomalous Hall effect. It's easiest, I feel, to look at in a semi-classical picture, but it can be redone in the non-equilibrium picture and also with the Kugel formulas. And one of these is skew scattering, and this looks directly like just like Mach scattering that you did in classical or in quantum in your undergraduate courses. And so essentially you have some magnetic potential that scatters two electrons in different directions, and that produces that anomalous voltage I was talking about in the magnetic system. And so this was measured by a group in Halle, and this Kagoni material, potassium vanadium antimony, which didn't have a finite magnetic field, but because of this variation in the spin moments on that component. Let's continue. So this looked for a new way for the skew scattering, where previously you had something like iron, where you remove you have an impurity in this iron, you can have a scattering event that happens there that splits the spin up and spin down, and this happens in this super clean limit of what's called skew scattering, where you have a small amount of scattering events there. You also have this in the opposite limit, which is called this dilute Kondo limit, where you have a non-magnetic system and you add a magnetic scattering, and it produces also this anomalous Hall effect. And so what happened here is that you have this cluster of spins that have some direction or some chiral product on each of these triangles, and this also produces this skew scattering anomalous Hall effect. The nice thing is here, the system will be much more clean, and so you get a high conductivity with this anomalous Hall effect, which is also shown here. This is the experimental results shown here, with the dashed line going up as you increase the conductivity in the system. So yeah, that's the system is layered Kagome material. Then these are the DFT results, and on top of the experimental results, here's a DFT Fermi surface, and then this is the RPES data that was shown. And some of the work done by Raphael also, right? Yeah. And then beyond that, you have this intrinsic deflection, where this is just the Berry curvature, which we saw earlier with the spin Hall effect, shown by Raphael. And then the last case you have here is what's called the side jump scattering, which is typically considered an intrinsic mechanism because it's independent of the number of impurities, the impurity density in this case, and it also scatters electrons in a similar fashion. Good. So let's go into now this multi-band model from chromium platinum 3, which is this. To the next slide. Yeah. So before we go into the multi-band model, we wanted to look at going back to this case we had here, and so one thing that you can see is that if I simultaneously reverse the sign of MO and T, then I can reverse the sign of the anomalous Hall effect just by reversing the chirality of those wild points. And so that led us to thinking if we could actually bring two of them together, could we increase the size of the anomalous Hall effect by doubling the size? And that also leads to one other possibility where we reverse the chirality twice, and in that case cancel out the anomalous Hall effect. So one case can you cancel it, and one case can you cancel it. So first, let's go through the case of the well-known systems, which is where you have just two bands, and this is in this case of this Co3Sn2S2 sulfur, which is one of the more popular systems for anomalous Hall effect. And in this case, you have this nodal line without spinor coupling, and when you add the spinor coupling, that nodal line breaks up into two wild points, so plus and minus chirality, and you have this Berry curvature between those wild points. This is shown here, and a plane cross. And this anomalous Hall effect actually maximizes out to a little bit less than the model predicts. It's about 1,500, a little bit less than 1,500. And those wild points are about 60 millieV above the well, above the Fermi energy. Is there a question? Is there a question? Good, sorry. This is also seen in the Co2MnGa, which has also this very simple band structure with these crossings that gap the spinor coupling, and also have the Berry curvature in between those wild points, and it also produces this large enormous Lorentz effect, which is the counterpart of the anomalous Hall effect when you apply a thermal gradient to the external electric field. And then just to add a little bit more here, this Co3Sn2S2, once you start to bring it down in terms of as you make it a thick film, and this is usually about one or two layers, you can actually gap the wild points and get this quantum anomalous Hall effect that pops out this based on the theory prediction. And so then now when we start looking at systems that trying to essentially get multiple bands there, one of the first cases we looked at was this Co210 titanium 10, which is this Weyl compound. And what happened here was, although we're trying to get this enhancement, we actually got this cancellation, and this is due to these wild points changing chirality and space there, which you get Berry curvatures, a large amount and small amount that cancel each other out.
So these are two wild points that are very close to each
this
other.
one has more. Yeah, this is more. These ones are not close to each other, and there's many more than two.
Right.
Yeah. So I mean, the model we have 4 wild points in this case, but and the real systems you can have many more. Yeah. So it's a little bit tough to look at purely with these spaghetti plots. Good. Thanks for the question. Then we came to this compound. So as you can see before, I worked in quantity phases group, so a lot of Weyl materials, and so this was, me trying to go away from the Weyl materials here. And so this compound shows this XPG3, which is actually a very famous compound, chromium platinum 3, vanadium platinum 3, and manganese platinum 3, which is, I think, a lot for magnetic recording in the early 90s. So yeah, this is a cubic compound, which has the blue here show the chromium or vanadium or manganese, and this gray shows the platinum. Once you add the magnetism in, the wick-off positions are the ones in the direction of the magnetization changes from the one on the side, and that actually changes the total symmetry of the magnetic space group. And what we're doing here is we're starting from vanadium, and we use this virtual crystal approximation to change the nuclear moment on each of these atoms, or nuclear number on each of these atoms. Yeah? And so going from vanadium to chromium to platinum to manganese, we look at the magnetization here and the orbital moment, and the magnetization of the platinum. I'll show you the final results we got, but because we are also in Claudia's Feathers group, I went to a friend and said, hey, look, we see some nice results here. Can you also grow this? And so he grew actually many more samples than this, but these are the XRDs for the samples, showing the quality of the samples. I think they grew on aluminum oxide, if I remember correctly. And so the other thing that you see is also the concentration here of chromium and platinum actually change, and so that actually does have a lot of scattering results in the we'll see shortly. He also looked at the magnetization in these cases as a function of temperature and the magnetization loops. And so it's showing that the quality, there's good quality samples, and also has a very small hysteresis in this case. And then more quality control for the samples is this resistivity, shown for the same colors for the same two. There's a little hump here, which I don't know what it is. I think it's just maybe someone kicked the machine or something at the time. I'm not exactly sure. And then also the magnetic resistance shown here with these butterfly loops as a function of the external magnetic field for in-plane and out-of-plane directions of the sample. So let's go back to the Co3Sn2S2. This is quite a nice system which shows these very nice Weyl points that are off. These are the Weyl points I showed earlier in momentum space in the Brilliant zone. And then as you change the direction, it gaps due to this break in the C3 symmetry that the system has. Again, I showed this plot before. This is a Co2MnGa gallium, which has this very much simpler band structure than chromium platinum 3, but a little bit more complicated, but still it's very easy to find those cross systems. And then we have this chromium platinum 3, which is, in all these cases we show which spin-over coupling and without, and in this case it gets very complicated, and it's very, how do you digest that? How do you make sense of that? And so one part is using this anomalous Hall effect, which is shown here for the Berry curvature and the total sum here for the conductivity. And here we're looking at the vanadium platinum 3, and what we can do is what we're doing is highlighting these two red bands here and these two blue bands here, which go above and below the Fermi energy. And we calculate the anomalous Hall effect for those bands, which is shown as red here, and for the blue ones here shown in blue, and then this dark black line and behind is total anomalous Hall effect, and you can barely see it here because it's almost zero. With the blue, it's this dashed blue line is the rest of all the other bands, and for the anomalous Hall effect. The way this is calculated, this is the two red bands and the influence of anomalous Hall effect with all the other bands listed there. Just because this thumb here, so you're taking red band 1 and red band 2, and then looking at all other bands. So then when we go to chromium platinum 3, so two things that we're doing there is we're shifting the occupation of the Fermi energy, and then the other aspects we're doing is we're changing the curvature of those bands. And so then down here with this red, so now what you can see here with the red case and the blue case, is you also see some crossings here that pop up, but you can see almost exactly that this is going to be twice as large as the red. You do have some of this dashed black line, which is from everything else, but it's mostly the contribution from those 4 bands.
Question: when you change the Fermi energy, do you gain or you use the opposite?
No, so I'm changing the nuclear potential on the atom, so that changes the amount of electrons.
But in a
So I mean,
experiment, can you do that?
experimentally, they would be, how do you call it, alloying the material, right? So they're usually, depending on how they grow it, they're growing the sputtering like they did in this case, then they have, in this case, 3 different targets, right? So there's a platinum target, a manganese target, and a chromium target. And the way they would do that is they would put some voltage on these targets, and it would be the same amount for the same amount of time, right? So then you get half manganese, half chromium. And you want to change that. Yeah, but there's no gate there because these are metals. It's very hard to gate them, right?
So it's not a field, it's a whole.
These are films, but they are not. I mean, I wouldn't call them thin films. They're like 60, 80 nanometers, right? So they're reproducing both properties quite nice. Yeah. Did I answer?
Yes.
Good question.
So this is DFT? Is that
Yeah.
But you have to put in magnetism? Or is,
Yeah, it's magnetic. Yeah.
so so you do some mean field theory for the magnetism? Is that?
Yes, exactly.
Okay.
Correctly. Yes, very good question. Thank you. And then for completeness, we also look at the manganese platinum 3 where it reduces down again. So you see the maximum years, well, just in these 3 complete cases is in this chromium platinum 3. Where is it? Oh, the clock is here. Sorry. Okay, good. Yeah, so then we can look further into this. So we look as a function, now we can change this in different intervals between the chromium, platinum, magnet, and then the chromium, platinum 3, manganese, platinum 3, vanadium, platinum 3. And what we see, this is still the theory results. This is the blue curve is the anomalous Hall effect, which gets maximized almost at 2700, which is just below the maximum for 4 bands in this case, which would be about 3000. And then in the red is the anomalous Lorentz effect, which we usually calculate at the same time as anomalous Hall effect. And this is the magnetization I showed before. And then lastly here, what we have is, so these contour plots show the energy between those two bands, and when they become, when the energy of those two bands are 0, then that's shown in white, and then so this red line here is the nodal line that we see, yeah? And that comes from, and I should have put the band picture with it, that comes from the red bands.
Can I ask a question? You have the magnetization as a function of this substitution, and then at some point this blue curve is the magnetization of the.
This is the orbital moment.
It's the orbital
moment. So, in that case, I kind of just plotted this for completeness, but I didn't really see any correlation with the orbital moment.
Okay, but I also.
And also, we were also thinking more about the anisotropy of things, but that's a different story.
But all these guys are ferromagnetic.
Yes, all ferromagnetic. Yeah, all ferromagnetic. And they're quite large, right? So you have a moment going from 1.5 to 4. Yeah? And experimentally, all ferromagnetic also. Yeah, and then in the KX/KY plane, you have both nodal lines pop up from both bands. So this blue one and this red one. Yeah? And then if we look at, so now we have sort of a coupling, look at the Berry curvature and the complete rolling zone. This is what it looks like. It's kind of crazy. But that's what we're summing all over. But we can then plot those nodal lines on top of that spinner coupling, where you see we get most of the contribution from these guys. Good. Going back to the chromium platinum 3 case. So we match the red bands and the blue bands to separate boxes here, just because it's a bit easier to plot. And so this is all the Weyl points. This red and white are the plus and minus, and across the whole brilliant zone. So we didn't look only at the Fermi energy here, but we looked just through all of them. And then on the bottom we have it for the blue, and then this black line here is the nodal line that we saw earlier. The only thing that changes here is that nodal line without spinner coupling exists on all the faces, but because we have the spinner coupling, it gets broken on the sides and only exists on the top here. And that black line is right at the Fermi energy here. So this tells you the position of the Fermi energy. And then if we look at the blue case, these nodal lines here still exist, and they are either very low below the Fermi energy or cut to the Fermi energy like this one in the middle. Yes, sir, please.
So you like
I
complex picture? For example, if you're applying a little.
I don't like complex pictures. I would like an easier picture,
I
but
will imagine in an application, by something, you apply a pressure on your material, then the whole response, the whole property will change drastically. Because
yes and no. But that's almost coming up to the next slide. Yes and no. So that was the next slide. Yeah. So yeah, we want to look at some cases, right? So we start from this cubic, and one case is to start to strain it in terms of the z direction. And maybe I go back to that because you actually now, but you can kind of already see here, depending on which type of strain or pressure you apply, what's going to stay on. So when you start to do that tetragonal strain, you don't really change the symmetry drastically. You still keep a lot of these things that you see here. And then you can also pull it along. So you can pull it. There's several things we did here. So we pulled it along, or pushed it along the z-axis, pulled it along the body diagonal, or pulled it along the plane. Yeah. And that's actually shown here. So that's the cubic case, and that's just a compressive strain in all directions or expansion, which the anomalous Hall effect has changed drastically, which was expected. And then the tetragonal case is shown here, and it's as a function of that strain, which actually increases a little bit and then stays for the most part constant around this 2000 value. And then as we pull along the side of the diagonal, so this is almost like a shear, it's a shear strain. In this case, there it drops to about 1/2, and then also in this case where we start to pull along, the body diagonal also drops down to about 1/2. So this is the cubic case that's matches up here, and then as we start to strain it, it drops down, and in this case also. And then we can also look at the buried curvatures in those different cases and cases where it was maximized. So this is the case going from the cubic, the tetragonal, which shows a very similar case. The only thing that happens is that nodal line starts to come off with Fermi energy. And then this is the case for the shear strain, which still has those nodal lines, but less Weyl points in this case. And then last is that rhombohedral strain, which drastically changes the situation.
So you break all these nodal lines because you're breaking the symmetry.
Yes, exactly. This is my undergraduate student that I like to always talk about because he did a very good job. And went on to get the NSF, GFRP, and go on to Princeton. And also get some fellowships there. But one of the main things he did was look at the magnetic anisotropy. He wrote a code for this, which was, for the most part, it's been done for these two cases, but to do it for cases that are not these perfect crystal systems, a bit tougher. It is written down in some German paper, but he was able to translate it and write everything out quite nicely. Yeah. So, Galaxia has anisotropy changes, and actually, this is the reason that it was actually used for these optical recordings, because you have these actually very large anisotropy values. So this shows the cubic anisotropy, which comes out, and then you go to an in-plane anisotropy, and then you have an easy axis anisotropy, and then you go to easy plane.
These values are mid-EV for formal unit?
No, this is EV.
EV?
Yeah, so it's very large. Yes.
How these are Weyl points? These are all Weyl points.
These are Weyl points. This is the anisotropy.
How do you find them? Computationally, it's a nightmare to find Weyl points.
Yes.
Because you don't know whether they cross or not.
Huh? No. I mean, the one you're taking a case and you're
because you don't know if they hybridize.
Huh?
You don't know if they're protected. Well, I don't know. If I go and calculate, I don't know if I have a Weyl point or it's just something that looks like a Weyl point, but I don't know because I'm plotting points, so I don't know.
Oh no, but you go in and you look at the spin characteristic. Right? So you have more points than this. You can also have other degenerate lines that are not actual nodal lines. And you get to go in and look at the spin characteristic of that, and then calculate the winding around that spin characteristic. Right? That's how you do it. I mean, there's a picture of the slide that shows some of them, but yes. Many of these are, I would say, not relevant because they're so far above the Fermi energy for the transport, but I was not so interested in what was relevant. Good. Back to what is relevant for the experimentalist. This is the experimental anomalous Hall effect as a function of the experimental Hall resistivity as a function of the external magnetic field, that's shown here. And then we separate that using fitting these results. And so as we change this resistivity, we're just changing the temperature there. And so then we can separate this side jump and the skew scattering, the side jump and the intrinsic shown here, and then this is the skew scattering shown here. Yeah? And so in some cases, the skew scattering is actually quite low compared to the intrinsic, but it can also jump drastically. And then we plot that as a function of the longitudinal resistance, and I'm going to go into the next slide. It's a bit bigger, I believe. Yeah. So we plot that as a function of for the two different samples from the experiment. That's the ab initio results shown there as a function of the longitudinal and the Hall resistivity. And we then took all of the other films that are interesting. So you have the iron film, which is shown here, which shows this intrinsic behavior, meaning that it is purely due to the band structure. It doesn't change as a function of the longitudinal conductivity. And then as you go to higher values or cleaner systems, you start to go into that skew scattering regime where it becomes sigma squared dependent. And then you have also this nickel film, which also is very intrinsic. You have cobalt, and you also have this gadolinium. Then on the other end, which has the small conductivity regime, you have the Co3Sn2S2 film and the Co2MnGa gallium film, and these have very small conductivity because they only have that single band there close to Fermi energy, so the density of states is small. And then directly in the middle, you have this chromium platinum 3, which is due to those two bands that we discussed, and matches actually quite nicely with the DFT results.
This graph where you would like to be in terms of application.
I would say somewhere here, right?
Then
But as I'm biased. No. In this case, I was ready to, in terms of applications, you want to, I think the next thing to think about is how much can you increase this, right? So can you do, four sets of bands in this case, and how stable is that?
but you like to be on the diagonal in the sense that
Well, it depends on the type of application, right? So this is a tough regime because you want your samples to be very pure and clean, right? If you want to use and you can use the topology there, but then it has to be very clean system, yeah. And so then you get into like this trouble of like, quantum Hall effect where your system has to be very, very clean to see it, right? This is this also in this regime you need it to be very clean to see the topology. And so this Co2MnGa gallium here I think is a very dirty sample. And there is some trouble, even though this is my friend that also grew that sample and these ones. I would still say that they're not very good quality. These ones, this is nice because it seems that you can always have a little bit of bad quality and still recover the physics. So that's why I say this is a better case because you can make make mistakes multiple times, right? In this case, yes. Good, thank you. That's the end, the summary. Hopefully it was not too long. How much time was that?
You started at 20 past, so you have time. But I have questions. We have questions, so.
Yeah, there's questions also. Yeah, so that's the summary. So that we went over, and if there's any questions.
At first.